Chapter 19. Aldehydes and Ketones. Nucleophilic addition reactions. Aldehydes and ketones are characterized by the carbonyl functional group, CO double bond, which occur widely in nature as intermediates in metabolism and biosynthesis. Much of organic chemistry involves the chemistry of carbonyl compounds. They are intermediates in synthesis of pharmaceutical agents, biological pathways, numerous industrial processes. An understanding of their properties is essential. If at least one side of carbonyl group is hydrogen, then this is called aldehyde. The simplest one is both sides are hydrogen, and this is called formaldehyde. Now, if both sides are carbon, and that's a ketone, and the simplest ketone is both sides are methyl group, and this is called a dimethyl ketone or acetone. Nomenclature. For ketones, choose the longest continuous carbon chain that contains the carbonyl carbon. Number from the end of the chain closest to the carbonyl carbon. Ketone ending is ONE, on. Here are some examples. The first molecule longest chain is 6, and so it's a hexane. The E becomes ONE, so hexanone. Now, if we number from left to right, we give the carbonyl carbon number 3. If you go from right to left, then the carbonyl is number 4. So we go from left to right, and therefore the name is 3-hexanone. So this means number 3 has a carbonyl carbon. In the second molecule, the longest chain is 6, and it has a double bond. If we go from left to right, we give the double bond number 2, but the ketone is number 5. All right. If we go from right to left, we give number 2, carbonyl carbon number 2, and double bond number 4. Since carbonyl carbon has the priority, so we go from right to left. All right. And this molecule is hexene, so its number 4 has a double bond, so 4-hexene 2-on. So 4-hexene 2-on, number 2 carbonyl on. Okay, it's a carbonyl at number 2 carbon. Now the next molecule has 2 carbonyl compounds, so it's a dione, and the number 2, number 4 have carbonyl groups, so the molecule is 2,4-hexene dione. The naming of aldehyde is similar to ketone. However, the ending, instead of ONE, it's AL. And also, in an aldehyde, the carbonyl one side must be hydrogen. So this carbonyl carbon is automatically number 1 carbon. Here shows 2 examples of aldehydes. In the first molecule, the longest chain is 5, so it is a pentanal, and the carbonyl carbon is number 1, so 1 pentanal. And for this simple aldehyde, 1 can be omitted, simply called pentanal. Now in the second molecule, the longest chain is 1, so 1, 2, 3, 4. Note that we put carbonyl carbon number 1 carbon, and so the name should be 2-chloro 3-methyl-butanal. Here shows some common names of aldehydes. The simplest one is aldehyde with 1 carbon, which is called formaldehyde. Systematic name methanal. Note the formula CHO suggests it's aldehyde. The structure is CO double bond with H, and the formula is CHO, and that suggests it's aldehyde. In comparison, if we write as COH, that means it's alcohol. For example, CH3OH, that's methanol. Okay, aldehyde with 2 carbon CH3CHO. Okay, suggest it's CH3COH. Okay, the name is acetaldehyde, and systematic name ethanol. All right, and the corresponding alcohol is CH3CH2OH, and that's ethanol. A benzene with one carbon aldehyde is called benzoaldehyde. Note CHO, so it's benzene with CO double bond with one H. Okay, so benzoaldehyde. This chart shows the relationship between ketones aldehydes with other functional groups. Ketones aldehydes are lower in oxidation level than carboxylic acid derivatives, and therefore they can be synthesized by reduction from esters and acid chloride. Ketones aldehydes are higher in oxidation level than alcohols and alkenes, and they can be synthesized by oxidation of alcohols and alkenes. They are in the same level with alkyne, so they can be synthesized by hydration of alkyne. Aromatic ketones or aldehydes can be synthesized by Friedcraft acylation reactions. In Organic 1, you learned alkene ozonolysis. Ozone molecules can cleave carbon-carbon double bond and add oxygens to both sides, give you two carbonyl compounds. If the alkene has at least one hydrogen on the molecule, the product will be an aldehyde. Otherwise, it will be a ketone. The reaction undergoes two steps. The first step, alkene is treated with an ozone molecule. This will form two intermediates, a molazonide and an ozonide, followed by the second step, reduction by zinc, give you the two carbonyl compounds. Here shows an example. This molecule is treated with ozone, followed by zinc reduction. The double bond cleave, add two oxygens. The left side is a ketone, and the right side is an aldehyde because the right side carbon has two hydrogens. As you already know, when an alkene is treated by mercury acetate and water, followed by sodium boron hydride, a water molecule adds to the double bond. According to Markov-Nikov rule, hydrogen goes to the carbon that has the most hydrogen. In this case is the right side, and the hydroxy goes to the second carbon, which only have one hydrogen. The product is an alcohol. In this case, it's a secondary alcohol. Similarly, when a triple bond alkyne is treated with mercury ion in acid solution, the product is also an alcohol. In this case, the second step, sodium boron hydride, is not necessary. Suppose we write this as R group, so the product should be R, let's write here, R, C, double bond, H2, because we start with triple bond. After we add water, it still have a double bond with OH here. Okay, now this is called eno. Eno, because you have a double bond and hydroxy group. Okay, eno is not stable, which undergo hydride shift. This hydrogen shifts to this carbon. Pi bond goes to here, forms a CO double bond, and the result is a ketone with a methyl group. The end carbon becomes a methyl group, and this is called a methyl ketone. Hydration of alkyne in the presence of mercury ion is a general method to make methyl ketones. Aromatic ketones aldehydes can be synthesized from benzene using Friedcraft acylation reactions, as you learned in chapter 16. The acetyl group is added to the benzene ring with the help of aluminum chloride as the catalyst. Ketones can be synthesized by oxidation reactions from secondary alcohols. The oxidizing reagents include chromium oxide, sodium chromate, potassium permanganate, and some mild oxidizing reagents such as Dess-Martin periodinane. Aldehydes can be synthesized by oxidation reaction from primary alcohols. The oxidizing reagent can only be mild oxidizing reagents such as Dess-Martin periodinane. If strong oxidizing reagent such as chromium oxide is used, the aldehyde produced will be oxidized further to carboxylic acid. Aldehydes can also be synthesized by reduction reactions from functional groups of higher oxidation levels such as esters. Alkoxides serve as a leaving group. Hydride attack carbonyl-carbon, leaving group leave, give you aldehydes. The reducing reagent must be strong enough for the reaction. Sodium boron hydride is too weak. On the other hand, lithium aluminum hydride is too strong. It will reduce aldehyde to alcohols. The appropriate reducing reagent is DIBAH, or diisopropyl aluminum hydride. A related reaction is to convert an acid chloride into a ketone by lithium diorganol copper reagent, or Gilman reagent. Chlorine as a leaving group, the carbanion attack carbonyl-carbon, leaving group leave, give you a ketone. Note that if we use Grignard reagent, the carbanion will attack twice. First give you a ketone, and then this attack second time, the final product is an alcohol. And therefore, if we want to make an aldehyde from an ester, we need a DIBAH, not sodium boron hydride, not lithium aluminum hydride. If we want to make a ketone from acid chloride, we need a Gilman reagent, not Grignard reagents. In summary, ketones aldehydes can be synthesized by oxidation reactions from alcohols. Primary alcohol give aldehydes using Dess-Martin periodinane as oxidizing reagent. Secondary alcohol give ketones. Ketones aldehydes can also be synthesized by ozonolysis of alkenes. Ozones cleave carbon-carbon double bond, add oxygen to both sides, give ketones or aldehydes. Aromatic ketones aldehydes can be synthesized by Friedel-Crafts acylation reactions. Alkyne hydration reaction give ketones. If alkyne is terminal alkyne, the product is methyl ketone. Aldehydes can also be synthesized by reduction reaction from esters using DIBAH as reducing reagent. When acid chloride combined with Gilman reagent, the product is a ketone. Here are the homework problems.